Okay, so welcome back to this next video in which we are discussing experimental methods for investigating exocytosis. Okay, so we've just discussed an imaging technique, which is the use of total internal reflection fluorescence microscopy. Okay, and I don't think what I stressed enough here is that what you're going to be doing here is taking multiple pictures of this. You're not just going to be taking one picture, you're going to be taking multiple pictures and then putting them together in a stream to effectively make a little video of the exocytotic process. Okay, so you can actually visualize the exocytosis process using this technique. The problem, the limitation to it is that the time lapse between two images is quite a long time, basically. Okay, it takes a long time to take each one of these photos. Okay, so the video is quite fragmented that you build, basically. And when exocytosis, especially in axon terminals, is occurring in milliseconds, it's a little bit difficult then to capture that process with a camera that has such a large time lapse between two photos. Okay, still, it is a useful tool. Right, so the final two techniques that I'm going to tell you about are other ways of measuring the exocytosis of vesicles in real cells. So one of them is capacitance measurements. You can measure the change in capacitance across the cell membrane of a cell. Okay, the other is by use of amperometry, which is basically a way that you can measure the amount of neurotransmitter that has been released in certain cases for neurotransmitters. Okay, so we'll start off with capacitance, measuring changes in membrane capacitance. Okay, so let me firstly explain what is capacitance. Okay, so let's have a cell here. Okay, so we all know that cell membranes have an electrical potential difference across them. Okay, there is a difference in the electrical potential extracellularly and the electrical potential intracellularly, and we call this the membrane electrical potential difference, or the membrane voltage. Okay, and this is usually around -65 millivolts, and what that means is that if you move from the extracellular compartment to the intracellular compartment, the electrical potential goes down by 65 millivolts. Okay, so if I give some symbols here, let's denote the electrical potential extracellularly as capital E subscript E, capital E for electrical potential, subscript E for extracellularly, and let's denote the electrical potential intracellularly by capital E subscript I for electrical potential intracellularly. Basically, if I move from here to here, this number, the electrical potential intracellularly, is smaller than this number, the electrical potential extracellularly, and it's smaller by 65 millivolts. So I can show this on a little graph here, or a little diagram at least. We can have the electrical potential extracellularly at this level, and the electrical potential intracellularly is at this level, and then basically when you step from one to the other, you go down by 65 millivolts. Okay, so this step down here from extracellular to intracellular involves a drop in electrical potential by 65 millivolts. Okay, right. Now, capacitance, the motivation for understanding capacitance is you have this electrical potential difference across the cell membrane. Okay, how do you get that electrical potential difference across the cell membrane? Why is the electrical potential intracellularly lower than the electrical potential extracellularly? Well, the major reason for that is that you have moved positive charge in the form of potassium ions from the intracellular compartment into the extracellular compartment. Okay, so you've taken positively charged ions from here to make this one's electrical potential lower, and put them into here to make this one's electrical potential higher. Okay, so remember, basic law of physics, wherever you stick positive charge, that makes the electrical potential higher. So if you've nicked positive charge from the intracellular the intracellular compartment, that's going to make the electrical potential here lower, and if you dump it into the extracellular compartment, you're going to make the electrical potential extracellularly higher. Okay, so that's how you have created this electrical potential difference here. And you can imagine that they both started off in the middle here, neutrally. Okay, So this one is the electrical potential extracellularly, and this one is the electrical potential intracellularly, and then we move the potassium ions out of the intracellular compartment. That took this one down to this, and then we've moved them into the extracellular compartment. That one took this one up to here. So the question then is, how much charge did you have to move to create an electrical potential difference across the cell membrane of negative 65 millivolts? How many potassium ions did you have to move, basically, to get this electrical potential difference across the cell membrane? And that, the relation there, is where capacitance comes in. Basically, the equation is that to produce a certain change in voltage across the cell membrane, the amount of charge you have to move, delta Q, this is how much charge you have to move, is going to be equal to the capacitance of the membrane times delta V. Okay, and I'm afraid my pen's going, so I'm going to call it there for this video, and we'll continue this discussion in the next video.